welcome to the panel. I guess I just want to say a little 1 minute preamble, and then I'll let the panel introduce themselves. And that is that the relationship between neuroscience, cognitive social, psychology, computer science is really foundational. And reading about this again before the panel, it's very striking to remember or to recall that really the earliest pioneers of AI drew direct inspiration from the brain. There's the first paper by McCollin and Pitt. McCollin, I guess, was a psychologist. Pitt was a logician. So they come from psychology and mathematics, and they proposed a mathematical model of a neuron and really laying the foundation for the neural nets today. And then there's the work by Donald Hebb, a psychologist again, which gave rise to the whole scientific theory of synaptic plasticity, and then leading up, also influencing, I guess, the backpropagation algorithms by Hinton and others. And this symbiotic relationship hopefully is going to deepen over time rather than weaken. And certainly, I think it's very clear that neuroscientists are going to take a lot of advantage of AI tools, and it'll be interesting to hear what AI tools would be useful, and also in reverse, that they will continue this fundamental inspiration. Okay, so I want to do it like this. First of all, you introduce yourselves very quickly, but there are two people that haven't given talks today. Now let's go forward. And that is starting with Kostas on the left here, and Nicolas second from the right. So everybody will introduce themselves, but you guys can take like 1 more minute to say what you work on, because we haven't heard from you yet today. So Kostas.
Cool. Yeah, hi everybody. I'm Kostis Daskalakis. I'm a faculty at MIT, and I'm in the Theory of Computation group, interested in algorithms and complexity with applications to multi-agent interactions and high-dimensional probability and statistics. In the last few years, I'm interested in multi-agent machine learning. So how you make AIs that are robust to either interactions among themselves or interactions with humans. And I'm investigating sort of like which of the paradigms of machine learning that we've seen very successful over the past decade or so carry over to the multi-agent setting, and also what of the foundations of game theory translate to the multi-agent setting when you have complex systems with that are modeled using neural networks, which makes sort of like the objective functions and the strategy spaces complex, and in particular makes a lot of these models not classical game theory, not very applicable. So that's one sort of like direction, so robustness to multi-agent interactions. The other thing that I'm very interested in, closer to high-dimensional probability and statistics, in particular generative models, is around how to train models when you don't have good data, or more generally when you have heterogeneous sources that have different quality of data. And in particular, that's the topic of a talk that my postdoc Yannis Daras, who's sitting back there wearing white, is gonna be talking about. So he's gonna be talking about how to train tomorrow morning, the second talk, I think, how to train diffusion models when you don't have access to good data, when you only have access to corrupted data, or when you have sort of like combinations of clean and corrupted data. And sort of like the motivation of this talk is that, like in many domains, many scientific domains, you actually don't have easy access to lots and lots of data. Or sort of like in other applications, you might not want to use data that you have because you want to protect privacy or copyright of this data. So the question is, like how can you squeeze statistical power out of corrupted data? So if you're interested in that, please come to Yannis' talk. That's all I had. Yeah. Thank you.
Hi, I'm Tatsu Hashimoto. I gave a talk earlier today. I work in the areas of statistical machine learning and natural language processing. I'm really interested in foundational questions in machine learning, like how does transfer work, like why does self-supervised learning generalize, and also empirical questions in natural language processing, like how do we make better NLP systems.
Hi, I'm Daniela Kaufer from UC Berkeley. I'm a neuroscientist. I actually trained in biochemistry and molecular biology, and then went up to look at systems and whole organisms. And what my lab is studying is brain plasticity in all those different levels. And what I described in the talk this morning was our sort of shift in perspective, where we're now asking, what can we learn from the resilient animals? So not only what can we learn from pathology, but can we understand what are the natural processes where the brain and other systems heal themselves in response to adversity?
I'm Adam Clivens, faculty in the computer science department at UT Austin, and I'm interested in algorithms for machine learning, theoretical computer science, and AI for protein engineering. That's it.
I'm Nikolaus Kriegeskorte. I lead a lab at the Zuckerman Mind-Brain Behavior Institute at Columbia, and we study the visual system of primates, including people and monkeys, macaques as well. And we build neural network models, recurrent neural network models that are meant to capture the computations that go on in the primate brain. So these are computer vision models in the sense that they can perform visual tasks, but they are supposed to perform these tasks using a similar algorithm as that used by the human brain and the macaque brain. So we compare these neural network models to neural activities that we measure in humans and macaques with neural recordings and functional imaging, and also to behavior. So we come up with tasks, visual tasks, where people view stimuli, they respond, and then there are detailed patterns of reaction times and errors across many different images, and we try to present these same images to our algorithms and predict these detailed signatures of their behavior.
Hi, everybody. Is this working? Maybe not.
Mm-hmm.
Okay. So my name is Yael. I wanted to add first to your list of computer science and psychology collaborations that Sutton and Bartow, who started reinforcement learning. Rich Sutton came from psychology, and Andy Bartow was in computer science. So goes back to that too. So I am basically a reinforcement learning theorist by training. I was just telling some students in the back that I did my first experiment at the very end of my PhD. I was completely a theoretician, theoretical neuroscience, computational neuroscience. And then I did my first experiment, and there was no going back, because clearly if you can, if you can test your own theories, then that cycle of the test then develops a new theory, et cetera. So I fell in love with that. And my lab, when I started my lab, we were mostly working on that problem that I mentioned at the end of my talk of basically, who gives us a state space? How do we learn a state space for reinforcement learning? With the thought that the reason that humans are so good at learning, and animals too, is because we represent tasks in a way that makes them easy to solve. Because we can represent them in a way that makes them really hard to solve, needs a lot of data, but we can also sometimes find very easy representations. And so we were really interested in that, not at all thinking about mental health. In fact, I don't think I read a single paper on mental health, until 7, 8 years ago, when I heard a talk where Klaas Stefan actually said, psychiatry is in crisis, and it's our fault because we've made a lot of headway in understanding computational processes, high-level computational processes in the brain, but we don't talk to psychiatrists at all, and there's no transfer of that knowledge. And I was just convinced by his that one sentence in his talk, and changed my focus to using these same tools and the same stuff that we know how to do in my lab, learning and decision-making, models of learning and decision-making, and apply them to mental health.
I have a couple of questions, but then the audience is going to join in and ask questions. And I'm actually going to start from specific and then we'll go to more general. So I guess the first question is one of the topics that interests me and I think was a thread throughout the day is this whole question about resilience or robustness. And I understand that you all come from different disciplines, and just wanted to kind of shortly, if you just put you on the spot and ask, what does resilience or robustness means to you in your own area? And some prompts to think about, is it like a fixed architectural property like redundance, or is it dynamic? That's, for example, in the talk of Daniela, it was sort of more of a dynamic thing, and I wonder what thoughts does that provoke in your heads now, those who don't do that right now. Another thing is, in what Adam talked about, he talks about adversaries, adversarial shifts, and is that really relevant to neuroscience to think about robustness in an adversarial setting or not? And then how do you actually evaluate robustness, which would be, again, something which might be different in different domains. So that's pretty open-ended. Robustness, resilience, and what do you think about it across these different domains, whether it's computer science or neuroscience? And I guess whoever's, we can go in order, we can go random order, we can go in like the might is right in the sense of whoever jumps first. No, nobody's going to say a word. Okay, Costas.
Okay, cool. It's a broad topic, and it's all sorts of things. Starting with generalization, you have a bunch of observations of the world, and you want to build a model that is not just memorizing what you saw, but it does well on a new situation. Now, this new situation could be from the same distribution as the one giving you the data, or a new setting that you haven't seen before. Maybe it's related to that. At the very base level is, being able to generalize from your observations to something, a new example or a new situation. And that falls inside it, generalizing the PAC setting, generalizing this kind of setting that Adam was talking about, generalizing, being robust to adversarial examples. But also other things that I would put inside the robustness and resilience is sort of being able to behave well in dynamic environments, understanding the impact of state to how you think about the situation, how you make decisions. Something closer to my own research is actually being robust to the presence of other agents. I think that's a big thing that we don't talk about enough in machine learning. We don't pay too much attention. The impacts is that agents are actually not that robust to manipulation by other agents or by humans. It's not even clear that our, coming back to your question, is it architectural? Is it about dynamic behavior? It's about.
Is there a program that kicks in? Yeah.
Yeah, it's about both, and it's also, I think, it's not even clear. I don't think even we have a good a good model of what should happen in a multi-agent interaction, right? Game theory gives us a lot of tools for either describing what happens in a strategic interaction, or from a normative point of view, what should happen in a multi-agent interaction. But unfortunately, in the types of settings that arise in deep learning, that is not applicable because of certain modeling assumptions that are typically made in game theory. For example, compactness of the strategy spaces or concavity of the utility functions. The moment you're operating in a complex enough setting where your strategies are not living in a compact space, or the utility you're trying to optimize is a non-convex, non-concave function, things fail from a game theoretic point of view. Like it's not clear what, from a normative point of view, what is the solution concept, while at the same time the standard machine learning approaches like gradient descent, trying to arrive at a local notion of stability, let's say, also fail. So of course we know that GANs are very hard to train using gradient descent. And that gets amplified by a lot when you have a non-zero sum game and multiple agents interacting. So I guess I deviated a lot from the main thread, but like other other aspects of robustness is that sort of like how much your models cater to subpopulations that are not as represented in the data, because it's a question of alignment. How much you can transfer, big models that require lots of resources at their inference time, to edge devices and resource-constrained settings. How much you can train with not a lot of data, with small amounts of data that related also to the talk that Yannis will give tomorrow. All sorts of issues. I think a lot of many items in the wish list of how to fix machine learning are, I think, related to robustness. Yeah, I'll stop here.
By the way, not everybody has the answer, of course. Whatever you feel like.
No.
Sure. So I think conceptually, I think of two different kinds of robustness. I mean, there's a spectrum, but I think it's useful to think about two different kinds of robustness. One is what I would call idealized robustness. This is kind of the ultimate goal of having a system that, operates, learns the right conditional distribution, the right predictive function under all inputs, right? And I think this is interesting because it connects to a lot of the grand challenges in machine learning of learning a system that really recovers underlying mechanisms of the world, right? You can operate in any environment, you can do all sorts of things. It's got connections to fairness. And I think this is also why I think robustness appears in a lot of discussions about machine learning deficits, because if you have idealized robustness, you have basically everything else, right? You have essentially causal mechanisms almost of how to do prediction. But I think this is a little bit too strong. I think the practical path to idealized robustness is probably non-existent. I've been excited pretty recently about what I would maybe call practical robustness, which is much more about, can you have a system that performs well under sort of realistic or even semi-adversarial queries that a user might want to enter into a system, right? Uses that people might want to have. And I think it's been an exciting time for machine learning and NLP because these systems have gotten good enough that people are really pushing the boundaries. I think one of the things about, ChatGPT and all these systems that people can interact with that's really interesting is if you look at the user logs for these things, they'll really push the boundaries of robustness. And I think it was kind of unthinkable when we were working on kind of more toy systems that we would have a system that we could deploy out to the world that people would stress test for us, and the systems would actually come out unscathed most of the time, right? And so this kind of practical robustness of interacting with users, being able to solve these challenging problems that people want to try to solve, I think is a really interesting problem. And I think it's inherently dynamic due to the nature of these kinds of interactions with user aspects of this practical robustness question. So that's what the second, more empirical side that I'm quite excited about.
So I think I said a lot about what I think is resilience in the mornings. You might have heard that. And if I summarize that, it comes down to plasticity, but really it comes down to remembering some kind of a balance between plasticity and stability, right? And so overplasticity, changing to everything that happens, means erasing some kind of stable traces of the brain that we would like to see continue. So both of those things need to be balanced, and they need to be balanced lifelong. Right? There's a lot of things that we learn from looking at successful agers, for example. If we look at those brains, those represent to me sort of lifelong resilience. There's a question of whether we take a snapshot in time and capture the very resilient individuals early on in life. Does that mean there's a cost for that even later on in life? So those are things that I think can parallel the systems that you guys are talking about.
I've been thinking a lot about benchmarks recently and how flawed they are. So like Tatsu talked about a lot of metrics in his talk about the AMY competition, but it turned out many of those problems were actually online. And so I think a reasonable theory for why these language models perform well is that it's just data contamination. We don't know what's in their training set. We don't know how much they've memorized, and we don't have a good metric for, and maybe this is more importantly, like we don't have a good metric for what a novel mathematical idea is. We don't have a semantic search for mathematics. Maybe even more starkly, like in the AI for health setting, I like to ask practitioners there, look, we know you shouldn't train on your test set. I mean, I think we all agree on that. So yes, we agree. But should your test set of patients be like 70% over, like your validation set, should it be like 70% overlap with your trained set, or like 40%, or should it be completely, should you just take the biggest validation set you have? And also, what does it mean for like a patient in your test set to be similar to a patient in your training set? You know, these questions are, nobody really understands any of these questions. So I'm very agnostic on language models. But I think this notion of like Tatsu was talking about, the language models can generate novel ideas. I don't know, I think about like the history of like the great composers. So we like to think of like Stravinsky and Debussy as like they came up with these, really, really novel, interesting musical works that out of nowhere that revolutionized the way we listen to things. But I don't know, maybe it was just incremental, and that they were also just making tweaks on like the canon of classical music that we no longer really know or listen to very well. So I think like what is novel and what is different, just those are very, very hard questions that we don't understand very well.
Yeah, I also think of out-of-distribution generalization when I think of robustness, and this is very central to our work. It comes up very often in different contexts. On the one hand, we want to be able to model the robustness of the primate brain, and I think at the moment the primate brain is still more robust in a lot of ways, for example, in terms of visual perception abilities than current AI models. So our goals, therefore, are aligned with the engineering at the moment. Eventually, we'll also want to capture the limits of robustness of the primate brain, right? And that'll be interesting as well. And another context in which it comes up is when we make predictions with our models, we can make predictions within the distribution that we've trained these models on or out of distribution. And out of distribution challenges, for example, testing with neural responses to different categories of stimuli, are very powerful for us to reject models, because sometimes it's hard to reject these function approximator models that are so flexible that they can sort of all emulate each other to a certain degree, right? And so in terms of methodology, using neural network models as implementations of computational theories, it's absolutely critical for us to optimize our experiments and to do out-of-distribution tests of our models. And one thing that fascinates me about the challenge of out-of-distribution generalization is that it's sort of an impossible ask. So because of the no free lunch theorem, which holds equally for within distribution and out of distribution, the only way that it makes sense is if the out of distribution test set is assumed to be generated by the same world. There has to be something in common, right? Otherwise it's impossible. And I think that points us toward looking for very general abstract inductive biases, so things, deep truths about the world that can be somehow embodied in our models. And this, for me, points back to cognitive science, where people have thought about what these very abstract inductive biases might be, such as space, time, objects, numbers, these very general concepts.
I just wanted to add one thought to this, which is kind of the tension between this general purpose idea of I'll have, one model that knows everything, and that it will also be tailored to specific populations, for instance, specific people interacting with it that maybe come from not from the majority group where the majority of the data came from. And I kind of wonder why we would expect one system to be able to do that. I mean, if we think of human robustness and kind of generalization and resilience, we each have our world model that's very tailored to the experience that we have had. So we're good at certain things, but take us to somewhere very different or to interact with people who are very different, and we fail, right? And maybe it's too much to ask of a system to I'll give you 95% of the data that are of this kind, but you should find out when you're in the 5% case and then respond based on only those 5% of the data. And I could say it could do that if you had latent causes because you could separate things, but we don't know that these AI systems separate things in this way. So maybe it's the wrong thing to ask it to do.
So I guess I'll follow up on what Nicholas started talking about. More generally, forget robustness or go beyond robustness and resilience. Can you think of ways that, obviously they're going to come, but are there some things that you could tell us about that you think that neuroscience or psychology can teach, AI at this time, sort of continuing this glorious past? It's hard to imagine anything glorious, right? No, just by definition, if it's glorious, then you can't imagine it. But what are things that come to mind? People talk about energy usage. That somehow, the brain, everything is down to a molecular level, so it's efficient. But we're certainly not efficient in our use of AI today. So this is probably more to the neuroscientists, but I'm curious what you have to say about it. What are the lessons that we are not really paying attention to, or I just don't know about?
Do you want to take that?
No.
So
I could start.
I think of. Do you want to start?
No,
You
sure.
start.
You go ahead.
So I think of multiple resource costs, right? So in machine learning and AI, there's been a focus on probabilistic inference, and that's a normative framework we all have in mind. And we have to remember that that is, on the one hand, very fundamental and very important, but also limited in that it's obsessed with just one of many different resources, namely data, right? And an animal is under strict constraints in terms of multiple resources. And I think of them roughly as falling into 5 categories, namely data, space, time, energy, and errors. So space would be how many neurons, how many connections, how big does the brain have to be, how heavy and large does the head have to be that you have to carry around. Time would be how long does it take to perform the computations, how long is your response latency or your control signal latency is very, very important. Then energy is the metabolic demand of the brain in a resting state, but also the energy that's necessary for particular computations. And then errors, of course, is how good is the behavioral signal, how accurate is the control, or how accurate are the inferences, right? And I think an animal has to balance all of these costs. And not only finally, but at each step of its evolutionary development, right? So it has to find a continuous path where all the solutions are sort of good solutions, and they're going to trade off all of these costs. And so to me, it's fascinating to think about how we can treat that as a joint optimization problem. So one reason why neural networks are so successful in AI, from my perspective, is that you define a computational graph and thereby define constraints on how many neurons there are, how many connections there are. You just have this limited computational graph, and then you minimize the errors, and so you can just impose constraints, right? But that is not the same as fully engaging the trade-offs between all of these costs. And so this is something that I'm very interested in.
It's really interesting that of the constraints that you mentioned, you didn't mention you didn't mention data in the world. How much data do you have to learn from or build on, which I think is the biggest constraint. Because
it's one of the
life
5.
is really slow. I mean, we just don't get that much experience. And I think, again, speaking of contrasting a general purpose mechanism versus I think we're a very specific purpose mechanism. We started neuroscience kind of started thinking, oh, neurons can compute anything. It's true, but they don't compute anything. They compute the specific things that they need to compute, and the circuits, I think, have been optimized to the tasks that we need to solve in the world. That's why, in order to be very good at chess, you need a lot of experience, but in order to do our daily life things, we don't need a lot of experience. So I think we are specially purposed for the things that we need to do to survive. And maybe one thing to take from that to AI is this idea of special purpose rather than general purpose.
So I guess on the same thread, I'd like to add that it's important to think better about embodied intelligence. I mean, what makes us learn faster, I would guess, I'm not an expert, you guys are the experts, but is the fact that as babies we're able to experiment in this world. Like what we're asking LLMs to do is to read about the world from someone else's experience and learn about this world. But the baby is actually throwing things on the ground, experimenting all the time, experimenting with its own body, with language, etc. Also like interacting with other humans. And I just think that these modes of learning are so much more powerful than just reading about the world. So that'll be fascinating to be able to carry over understanding from how a human brain experiments to bring those ideas into AI. But what I'm curious about, just to add my own question to the panel, is how much of that do we actually do understand in neuroscience or cognitive science, like in terms of then being able to take those ideas and put them into AI. That's what I'm not sure about, because I don't know about the literature and stuff. So
I would say not a ton.
I think it comes down to so many different levels. So you can understand that at the level of circuit that are changes. You can understand cells that are. You can look at local mechanisms that change. So all of this plasticity is how learning is achieved, and things that we don't necessarily think about, but forgetting. So there's no learning if you don't forget some of the things. There definitely has to be some selectivity and some salience that are put onto different things that you learn, and they're important versus others, putting the context into different things. But at the end, you have to think about changes constantly. There's functional changes, structural changes, morphological, different kind of cells. Even just the fact, to me, that when we think about, immediately when we take it to computers, we say neural networks, and we're not thinking about astrocytes and oligodendrocytes and myelination and all of those local mechanisms of control over what's happening. And then at the circuit level, we're already losing a lot of information there.
That sounds fascinating. I mean, this various granularities of controlling how much you want to learn and forget, so that you can learn a lot of tasks, forgetting what's not important anymore, and or not forgetting what's keeps being important and stuff like that.
Coming back to the efficiencies of learning and what you really need and what's not.
I must say, Kostas, that my reaction to your question about whether this idea with the baby doing actions and collecting information versus reading about it, maybe it's just a question of how much. So in other words, you might be able to learn it all from reading versus doing actions, but you need a lot more data than. So it's a question of how much, rather than that it's impossible to learn just from reading. That would be my theory. Because I was thinking about language translation. If you get lots of language versus do actions and then see what people say, it might be this just a question of how much data.
It is a matter of how much, but I mean, there are definitely inherent limits to what you can understand about the world from observational data. Like if a human has gone out and actually done the experiment of taking an umbrella out and seeing if it rains, versus seeing rain and taking an umbrella out. Like if the human has done this experiment and has actually gone to the internet and written down about it, then you can basically learn from that experience. If it's written in a way that the cause and the effect are clear. But obviously there are limitations to what causes and effect you can actually learn. Like I don't know. Like I mean, our interaction here. Like I'm not sure. Like how we're all reacting to each other's expressions and things like this. Like this is like an experiment that is happening right now. But I'm not sure how well it's written down on the internet. Maybe in some books and stuff like that. But
So one of the things that's super important in learning and in memory is the emotional valence of things that happen. And something that arises with a big emotion will be much more memorable, right? We used to say, where were you in 9/11? And people remember a lot of things. And then I said it in the class and I realized they were not. In 9/11. So, yeah, but you
What
know,
is 9/11?
emotional memory. So, so what's the equivalent of that, right? In any machine learning type of situation, is there an equivalent to an actual emotion? There's a recent paper that we just looked at, that we just found from a couple of weeks ago, where the LLM was given prompts that had a neutral story or a trauma story, and then given questionnaires. And in the questionnaires, they reacted with a difference in mood after reading a trauma story, for example. But what does that actually mean? I don't know. And does it change the encoding of that as if you actually do have an emotional response to it?
Are we going to start studying PTSD and LLMs?
Did you read this paper?
No,
so.
no.
It's an interesting one. It not only did it, try to do emotional. Not tried. They did emotional scale on as a reaction to those two different stories. But then they also had it was ChatGPT, and then the ChatGPT also got a mindfulness script, and that also changed their response to.
Sometimes my hidden theory is that there are actually humans on the other side.
It's like the little people on the radio. So, which I used to believe. I mean, I guess you don't even know what a radio is, probably. So. But actually, it brings up the question about one of the questions I wanted to ask about parallel experiments, which is one thing that Nicholas, I think you mentioned. If you have to set up a parallel experiment, are there some guidelines? Are there some examples of interesting parallel experiments that you could tell us about?
Yeah, I think that's a major thing we need to think about, because the primate brain has secrets to teach to engineering, but these are not secrets that we neuroscientists have uncovered yet, right? So we need to work together, I think, and working together on tasks that are interesting for computer scientists and also interesting for cognitive scientists and neuroscientists. That's a major challenge, and it's actually not obvious why those tasks, by and large, don't exist. You can compare the tasks. So usually computer science tasks are closely related to application domains. So they're often, lots of real images, challenging things, whereas tasks in neuroscience or cognitive science are often extremely controlled to the extent of having small, limited image sets, and generalization is just to different measurements of responses for the exact same images, right? So that's a major limitation of a lot of the scientific literature there. So we can help each other, I think, and if we can bring together people from both sides to envision better benchmarks, and sort of benchmarks that are infinitely generative, where you don't have like a limited set of stimuli, but you can generate infinitely, I think that could drive a lot of progress. So I loved your slide in the beginning with the disciplines. Cognitive science was one of them, neuroscience and computer science and AI. And those three disciplines we've been trying to bring together at this new conference called Cognitive Computational Neuroscience that Thomas Naselaris, Kendrick Kay, myself, and some others started in 2017 at Columbia University. And there, the focus is really bringing those communities together and thinking about things like shared benchmarks and stuff like that. So if some of you want to join, it's in Amsterdam in August this year.
Not Amsterdam Avenue.
Amsterdam.
Amsterdam.
Not Amsterdam Avenue, no.
Okay. So I'm just going to ask 2 quick questions and then open it to the.
I just want to be a little bit of a party pooper on that, and say that when I think about your question about parallel tasks, I ask myself, what's the research question? Like, do we have parallel research questions? Because often, when we design a task for the brain, we want the research question is about, how does the brain work to solve this? And is the parallel question, how does the LLM work to solve this? That's usually, that doesn't mean the same thing. Like, we want to understand the brain to fix it to all kinds of things because the brain actually is living. And I don't know that we have that kind of interest in the LLM. And so if the questions are not parallel, it's not clear that that it should be the same task.
When I said parallel experiments, I didn't say it was the same experiment. It might be aiming at the same task.
Yeah, so I just wonder, where is the parallel here? Like, what do you mean by parallel research questions, for instance?
I guess, one way I interpreted Shafi's question could be that, or one direction around this question is, artificial nets can work as existence proofs of a phenomenon, of explaining a phenomenon we observe on humans, but we don't really understand the underlying biology or neuroscience about how it happens. So, if we can replicate it in silico, that's at least like an existence proof, like one way this phenomenon can arise, and then we can formulate perhaps hypotheses even testable that we can go and do on the human brain. And I guess that would be like the one way to do that. In the opposite direction, the amazing abilities of the human brain are existence proofs that something in silico ought to be possible, even though even if we cannot attain it right now.
I would say there are areas in neuroscience where there's an alignment and parallel tasks and benchmarks can be really useful. And there are other areas where there's no alignment. If you're working on something in neuroscience that is not an interesting engineering problem or that's entirely solved, then engineers will not be interested. In my area, there is an alignment because the algorithm of primate vision is a mystery and it's better than current AI algorithms, right? And therefore, in that area, I think parallel tasks and parallel benchmarks have potential.
Okay, one I guess very quick question: as a neuroscientist, what would you like AI to give you? I know that you have this promise, AI will help us do better in neuroscience, but in my mind it's amorphic. Are there some things, specific tools that you would like this community to come up with? There must be. Or is it just like the great white hope?
I think I answered some of it in my talk, so I'll let you guys.
So for me, you're already giving us so much. The software tools are essential. Thank you so much. The software tools, the hardware, we need the same tools that you're building for your purposes, and that's great. And in terms of statistics, we also need to build our own stuff, of course, and collaborate. But for me, it's those elements those platforms that are really useful for modeling brain information processing also.
Yeah, we make heavy use of machine learning algorithms and that,
What type? What type of machine learning algorithms?
We do trial by trial model fitting, so we're using. I guess in those we just develop our own in the end. But I'll tell you one thing that maybe it exists and I'm shopping for right now. So let's say you have a large data set, and you want to make predictions in it, and those predictions can be linear or nonlinear, but that data set is probably not homogeneous. So the way we've talked about other data previously, but think of this like large clinical data set. Is there a machine learning algorithm out there that will give me automatically, like data-driven, here is the way to divide your data based, like these are the two parameters, and I have many parameters, many different variables about these subjects. This is a parameter by which if you divide them into groups, then you can make your prediction really well. Like I want to predict, treatment response from stuff, but I also assume that there are different subcategories in the data. So that's like a machine
So
learning algorithm. that
hypothesis generation, really.
Sorry?
So it's kind of a hypothesis generation.
No, it's kind of like a mixture of factor analyzers or something like that.
Yeah, mixture of experts. Exactly. So it tries to divide the data into different specializations. That each expert's a specialist in that area.
The thing is, I don't know which are the X and Y variables. I know the Y, but I don't know which are the predictors.
At the same time.
Okay, great. So that's the way that we use machine learning.
And I guess the last question, and then I'm opening to the crowd, is about ethics. And I guess it's, can you comment about what is the ethical considerations of research on individual differences, for example, with respect to mental health? I think that's more ETL, especially given... That's right. But more generally than that, what are sort of some ethical and philosophical implications of building machines that mimic humans?
Well, let me just point out maybe a slightly different aspect to your question that is very rarely talked about, and I think but I think it's an ethical point, and that is there are huge financial conflicts of interest when people talk about language models that are often unacknowledged, undisclosed. If you think about you coming up with a new drug, of course the FDA has to do clinical trials, but there are like supplements out there that are not FDA approved, and you can take the supplements if you want. But I think we should all be aware that doing better on like benchmark. It's unclear, what all the motivations of all the actors are, except that there are huge financial incentives, and that a lot of the benchmarks are there and don't change precisely because people know like, oh, there's a huge reward for me if I can continue to do well on this benchmark, even if it's not a good one.
Yeah, so we've been thinking a lot and don't have an answer for this, but about the issue of what happens if your algorithms fall into malevolent hands? And they will, right? Because there are all these actors who are acting out of a financial interest and not a goodness of people interest. So let's say we want to, in order to help people, we want to devise an algorithm that will predict which type of treatment will help you if you have depression. Well, that algorithm might also predict that none of these are going to help you and you're going to stay depressed. So what if a future employer just runs this on your online available, social media data and decides not to hire you because you have currently untreatable depression, and then your healthcare provider also decides to not give you any treatment because they're unlikely to work, et cetera, and they don't care about what error bar the algorithm gave. So I think it's really, really tricky. And one thing that we have avoided using is any publicly available data. We just don't want to develop algorithms where people don't have to consent to the use of the algorithm. But if we don't develop it, someone else will. And it's not like none of this guarantees that these algorithms, that basically we're not giving bad actors tools that can be used really badly. And also that we're not leaking any health information. So even if we literally, don't leak the information of our subjects, that doesn't mean that our algorithm itself is not something that people can use to infer health information about other people. So this is a big worry for me, and that's why I asked to bring this question into the panel. And I think it's something that the field should be thinking about, especially with these AI tools. They're so good at responding and predicting and doing all this stuff with publicly available data. It's just so scary. And we tend to think, like in our IRB applications, before we do an experiment, we think of the risk and benefit to the patient, to the subjects. But nobody calculates the risk and benefit to humanity at large of developing this thing. Is this study worth doing at all, or is this algorithm worth developing in terms of how badly it can be used? I don't think any of us know how to calculate that and how to make that decision about what research we're doing.
Thank you. So now I'm going to open it to the audience for questions. I think, Frauke, you had a question.
So, Daniela Daniela and Yael, you are studying flaws in the human brain and possible ways to maybe mitigate them. But we know that some of the flaws are there because they save energy, for example, and you brought that up, that energy, or the research constraint in the monkey's brain. Are some of these useful learnings for the language models, and to which extent have knowledge about heuristics and stereotypes and all these things already bled into the development of these models, and is that useful, or do we right now still have too much energy that we don't have to learn from the flaws and apply them?
I guess I can initially react to that, and maybe my learned neuroscience and cognitive science colleagues can step in. But I think we don't really need any more help learning heuristics. Like, the models are pretty good at heuristics. That's kind of the first order things they capture. I do think there's been a lot of interest in kind of the energy and other kinds of constraints in the models. But a lot of the focus has been on the systems aspects of things, right? Like, how do we get better architectures? How do we make better hardware? And that has really actually been remarkably good. I think that has been much more of like the successful paradigm towards pushing efficiency, rather than let's make worse models that are somehow faster. Like, the models that sort of seem closer to that are things like sort of smaller models like cascades, so basically like deferring to small models, based on some like routing function. Those do exist, but I think right now, because of the deeper issues with robustness and reliability and just in general, getting the things right, it seems like, and I agree with this focus, that like really what we should get right is make sure we have a system that can do things, and then see whether we can apply either exact or nearly exact systems optimizations to get the energy usage down. That to me seems like the better path than to sort of build in the flaws and hope that the energy savings make it worth it.
So I have a question. Actually, I was thinking this is one of your points in or a response to a question you gave, Danielle, in your talk, was that there are some cases where maybe like robustness or resilience isn't optimal, right? So kind of being robust and resilient to everything isn't optimal. You want to remember that mountain lion and your fear from it. So I'm wondering to what extent that is a lesson, or that's something that is useful in our current models. So in other words, we always think about trying to build more robust models, more resilient models, models that generalize better out of distribution always, right? And so when is it better maybe to not be as robust or resilient? Does that lesson ever apply?
Well, I think some of the answer is at the level of a population, right? So if we come above an individual level and think about a population or system, then multiple different strategies are probably better than one strategy for it. If you try to make that into, and then if you take it into Yael's question about ethics, I had it makes me think about a very interesting particular point that came up by a student in a discussion that we had last week about the ethics of psychedelic research. So I said something about we're studying psychedelics, and it went into resilience, and psychedelics maybe mimic some of the resilience mechanism and so on. And the student said, isn't it better to have trauma sometimes? Because, was giving examples of people can use that to create the perfect soldier that have no moral values and no trauma. And you never remember any trauma, so you don't actually learn from that, and you go through life in a different, so I can imagine.
A tortured artist.
Tortured artists.
They need trauma to be able to create.
Maybe we will lose all of that. But it's clear that there's some things that come through that are better. But I think at the model of engineering, I would think as a system, you want to have different response mechanisms, when we think about population genetic adaptability of populations, it's always about having multiple response routes. So maybe not always the resilient one. And the resilient mouse.
Is there any conjectured reason why at an evolutionary level you would like non-resilient humans to stress, for example? Is there any conjecture?
Yeah, so the answer I gave at when asked at the lecture was this non-resilient phenotype, it actually tells you something about the environment, or it is something that is programmed by the environment. And in fact, it's programmed by the environment through multiple generations. And I don't know who I talked to about early life stress and maternal behavior that we talked, and we used to, in the beginning of that, people would say the bad moms and the good moms. Okay, the good moms were the ones that sort of their behavior made a resilient individual, and the bad moms are the ones that got the individuals that were that had lower cognitive abilities and higher stress reactivity and all that. But it's not a bad mom. It's a mom that had a lot of unpredictability in its environment, and therefore programs an offspring that now is more careful. Meaning you're not going to be resilient, you're going to be anxious, therefore you'll survive in an unpredictable, unsafe environment.
So I think the answer is really on a population level. So if you have all these strategies altogether, somebody will survive, but specific ones may not.
I also want to say that you mentioned flawed brains or flaws in the brain, and I think a lot of the flaws are not in the brains, but in the environment that these brains end up being in. So I don't even like the term, definitely not mental health disease or disorder. I just say mental health condition and I don't think it's necessarily something that's flawed in the brain. The brain might be doing might be working the way it should work, adapted to environment A, but it's stuck in environment B that it was not adapted to. And so when we're trying to think about, so that's exactly the point, that the flaw that we see is telling us what we should fix in the environment, not what we should fix in the brain.
Go ahead.
Oh, thank you. It also seems like this kind of concern, at least in the context of building AI systems, becomes more relevant once you have sort of continual learning and like systems that are deployed out in the world that are learning from experience. Because then you might start thinking about things like, oh, we should have like multiple kinds of agents. We should have them learn with different levels of risks. And then it becomes sort of this population level question. But I think the current systems now are very static. Like a person comes in and updates it once every 3 months. In that case, maybe you don't really have this notion of like a diversified population with different losses.
Do you want to say something?
I was going to say a good example for that is developmental programming of metabolism levels, right? And so we know that if the mother went through the pregnancy in times of food scarcity, there's a programming of the individual to keep any kind of food. If the individual now grows up in an environment B that has enough food, this individual is going to be obese, right? So the programming and the environment is here what is the key. And so when you engineer a model and it's not dynamic to the environment, then that's where the flaw.
I had a question. Oh, right here. In line with the ethics, I wanted to hear your thoughts on Neuralink's AI chip that are in clinical trials right now for people who have paralysis or neurological disorders. Do you think these chips, AI chips, should be limited to, the disadvantaged populations, or would you say that it would be beneficial to have them for regular people to enhance human capabilities? What are your thoughts on that?
Let me start. I'm not an expert, but let me start. And I think actually this is one of the very interesting things that this interaction between AI and neuroscience can give. I think it's a very important application, but I definitely share your concerns about the risk that arises the moment this interface between computers and the brains actually happens. About the ability of the cloud having access to our internal thoughts and stuff like that, as well as controlling our thoughts. So I don't know when we're going to get there, but definitely I see a lot of risk when that interface is good.
Any final thoughts? We're almost out of time. I have a final thought, and that is that somewhere we've talked about industry, financial gain, as a motive in studying one thing or another. So I guess one of the things that I think that university can still do better, I mean, many things, but it's one definitely, and that is that I doubt that half of OpenAI is going to be neuroscientists. So I think that the collaboration, between computer scientists, neuroscientists, psychologists, is much more likely to happen in academia, and it's something that we should sort of capitalize on and do. So if this will change a little bit how academia works, I think it's all to the good. So that's the
Get
final
Simons
thought.
to fund
What?
it. And we should get Simons to fund it because NIH.
Simon's Foundation. Yeah, well, go for it. I'll definitely come with you.
And that's right.
That's true. Anybody else wants to make some final comments?
Maybe on the Neuralink question or brain-computer interfaces more generally, from my perspective, there's been a lot of progress with them in recent years, but we also have evolved input and output devices, right? For example, here we're using our eyes and our ears and our voices and our bodies, and these are really amazingly good. And so, to me, it's not obvious how that will be easily beat with brain-computer interfaces given current bit rates, right? I think eventually, these ideas in these directions are going to be important, and it's good to think ahead of time about the ethical implications. But it is amazing how well just face-to-face interaction and vision already works, and that's a high bar.
Okay, thank you, and thank you.
Thank you.